Okay, so section 6.1, we're taking a look at just more about areas, but more specifically, we're looking at areas between curves. Okay, so before we do, I want you guys to have a separate, like whatever else you would take notes on right now. This is just our example, so that you don't have to like draw graphs and stuff. So have whatever else you would normally take notes on out, so that you can kind of supplement as we go. Okay, so I'm going to actually bring this back up in just a little bit. We need to kind of think about how we can find these areas first. So I'm going to write this here, section 6.1. I'm going to call this area between curves, even though that's not the exact name of the section, but that's what it's about anyway. Oh, let me take over your guys' screen. Okay. All right, so let's go ahead and say, I'm going to start with just kind of a picture. Let's say that we have two functions, f of x and g of x. And let's just draw kind of some arbitrary graphs. The thing that we're trying to look at here is not just finding area, but finding the area between two different curves. So let's say I have my x and y axis, and maybe I have some function f, which I'm going to make green, and some function g, which I'm going to make purple. And let's say we want to find the area between those curves on an interval from, let's say, A to B. Okay, so let's go ahead and start by visualizing the area. Okay, so visualizing the area. So can you guys kind of visualize the area between the curves? Now, I'm going to go ahead and just pause it for a second and just talk with someone next to you about what region would represent the area between the two curves. Okay, let's discuss as a big group now. So, again, we're trying to find the area between the function f and the function g. I'm just going to like throw a few things out here. Would it be this region here? No, because what is this region? This is the region, yeah, this is the region under g. I guess you could say between g and the x-axis. That would be this region here. Okay, so I want the area between f and g. So that would be, I need a good color. Let me grab, oh, I have a highlighter. Okay, so that would be this region right here. Okay, this is the region that lies between f and g. That is, it lies under f, but it lies above g. Okay, so we have the region in mind. This is the region between f and g. Now I want us to think about how we would find the area of this region. Pausing again, discuss. All right, so what do we think? How would we go about finding the area between these two curves? Thoughts? Ty, what do you think?
The area of the curve on f of x from A to B minus the area under g of x from A to B.
Okay, so we find the area under the f curve. The area under the f curve. This docam's killing me today. Trying to learn calculus here, docam. Get on with it. The area under the f curve. But if I did the full area, that would be all of this, right? This full thing. So I want to take away this area, which would be the area under G. So to find the area then, it would be, I'll put it this way. The area would be, I find the total area under F, which would be the definite integral of f of x from A to B. And then I want to take away the area from A to B under g of x dx. And I'm going to do a few, you know me, colors, highlights, all that fun stuff. Okay, so this would be the area under the green curve, take away the area under the purple curve. Okay, does it make sense why we would do it that way? Now notice that this one was first, and we subtracted this one. Why did the order go that way as opposed to me taking the area under g and then subtracting the area under f? I'm going to do a different person. Yeah, Nate says because you'd end up with a negative value, because the area under G is smaller than the area under F, right? So if you did it the other way, you'd end up with a negative. But the idea is that we're doing it this direction because we want the area between. Now, this curve is on top, and this curve, I guess line, is on bottom. So we want to generally take the top one minus the bottom one. Now, do you guys see how I could go about, if I actually had like equations for f and g, I could find this area, and then find this area, and then subtract them. But there's some common things here that maybe I could simplify the way that I write this integral. Because they both have the same bounds, right? And I'm subtracting the integrals. So what could I do? Yeah, I can combine them using properties of logs, but we're kind of doing it in the reverse order, or not logs, properties of integrals, but I'm kind of doing it in the reverse order that we normally would. So this can be written as the integral from a to b of f of x minus g of x dx. And that would generally be easier for us to evaluate. We would only have to do one evaluate at thing, and like it's just be a slightly less step. But sometimes it'll be much less steps if f and g have some common terms that maybe we can combine like terms before we even do the integral. Generally make things a lot easier. I want us to also think about how this integral relates to the area based on the picture that we have. So another way to kind of see how this ends up being another way of finding area. Remember back when we were looking at area in the first place, we were doing the triangle thing, right? We were saying, okay, we're going to put a bunch of triangles under the curve. The base is delta x. The height is the function. So we can integrate f of x dx. So similarly, if I think about putting rectangles in the region, here's just one representative rectangle. Okay, and depending on whether you choose a right endpoint or a left endpoint, I'm not going to worry about it too much because we're not actually going to be using rectangles. This is just for a visual. So notice that, I'm going to zoom in just a little bit here. Okay, what would be the base of the rectangle in general?
Delta x.
Yeah, some change in x, so we'll call that delta x. Now, if I were to find the height of this rectangle, because I want to find area, so I need the base times the height, what would the height be? Yeah, it would be whatever the y value is here minus whatever the y value is here. Okay, and the reason why that's the case is this y value would be this entire height from here up to here. Okay, I want this total distance, but without this length here. So I have the total distance, which is, I guess you could say I'll just say f of x. It's not notationally correct, but I don't care. And I want to take away this distance, which would be g of x. You might be thinking that I'm complicating things more right now. You're like, Stina, this thing was pretty intuitive. We don't need the rectangles. We're okay. But eventually when we start doing the volumes, you're going to want to be able to kind of visualize these rectangles, because when we start revolving, we're going to be revolving the rectangles. And so if we make sure we can visualize those rectangles, we'll be able to visualize what the revolution of the rectangles would be. Okay, so that's another way of seeing that, is that basically we're taking all the base times the height. Now the height is f of x minus g of x, and we're adding all those up. Okay, so we can kind of interpret it that way as well. Okay, so let's move on to some examples. Or actually, let me go ahead and write this one more way really quick, because this is going to get into another example that we do. The main idea here is that I don't want to use f and g because later on if I do an example and there's f is on bottom and g is on top, we'd want to take g minus f. You just want to take whichever curve is on top, subtract whichever curve is on bottom, and so I'm going to go ahead and write it this way. You want to take the y top minus the y bottom, integrate that with respect to x. Okay, all right, so let's go ahead and go to our worksheet with these ideas in mind. Use this. Okay, so let's start with the first example. So we have two functions, 4 minus x squared and x squared plus 2. Now I'm going to start by figuring out and now I happen to give the graph in this case. If you hadn't been given the graph, you really want to visualize these areas before you start. So don't want to just assume one thing's on top and one thing's on bottom. So let's go ahead and identify which one's which. So this curve, for example, which one is this? F or G? Yeah, this one's F, because I know it's a parabola. This one's facing downwards, which should be right, because it's a minus x squared. I see the y-intercept is 4. Okay, so I'm going to make that one green. And then, by process of elimination, this one should be G, but we can kind of double check. It's an upward-facing parabola. And, yep, its y-intercept is at 2, so that's looking good. Okay, so it says find the area enclosed by the functions f of x and g of x. And another way I could say that is find the area between the curves. It would be the same thing as the area enclosed by the two curves. Okay, so 10 seconds, talk with your neighbor. Which region is being identified here? All right, what region are we thinking? What's our interval? Yeah, like the region enclosed. So let's see, so it wouldn't really be this, because if I do this part, you see how this would just go on forever and ever? Like they're never going to kind of like come back together. So we see two intersection points for these two functions here, right there and there. And then this is the only region that gets captured by both of the functions. Okay, so this is the region that we're looking for in this case. So I'm going to go ahead and I'll highlight it. Kind of looks like an eye. Or Stewie Griffin's head. Kind of looks like that too. Okay, all right, so find the area. Okay, so using the idea that we just learned, we're going to try to integrate from A to B. Okay, I'm going to leave the A to B out right now. So f of x, I can tell, is on top. Got it? F of x is on top, so that'd be 4 minus x squared minus g of x, which is on bottom, so x squared plus 2. What's wrong with what I just wrote? Parentheses. All right, I'm subtracting that whole g of x. Okay, so I need parentheses around that. Now, do I know for sure that these curves intersect at -1 and 1? It sure seems like it. Very close, but to make sure it's not like -1.005 and 1.02, right? To make sure it's not that, I should just double check and make sure. So there's two ways that you can do this. One, well, when do two curves intersect each other? When does that happen? When they're equal to each other. So you can go through this algebraically. I'm just going to show you that real quick. If I did 4 minus x squared equals x squared plus 2, then I'd want to solve this. I'm going to add the x squared to the other side and subtract the 2 to both sides, okay? And then divide by 2, plus or minus 1. So x equals plus or minus 1. Okay, so that tells me for sure that these are, in fact, the intersection points. Another thing you can do is if you graphically see this and you're like, oh, it looks like -1 and 1, let's double check. So if I plug 1 into the f function, I get 4 minus 1, which is 3. If I plug 1 into the g function, I get 1 plus 2, which is also 3. Same thing would work for -1. Okay, so that lets me know for sure that my bounds go from -1 up to 1. Okay, and then now we're going to go through and integrate this, which is going to be the more straightforward part. Okay, so pretty much in all of chapter 6, it's going to be setting it up is the kind of difficult part, and then once you have that, it's pretty easy to evaluate. So we're going to go ahead and combine like terms. So I know that this would be subtracting the 2, so 4 minus 2 is going to be 2, and then I have a negative x squared minus an x squared, so that'd be minus 2x squared. And hopefully you can see that upper bound of 1 there. Okay, so notice that doing this made it much easier for us to, well, not much easier, but a little bit easier for us to evaluate the integral. So I want the antiderivative of 2, so it'd be 2x minus 2/3 x cubed from -1 to 1. You guys with me? Yeah? Okay, let's plug the 1 in. I'm starting to run a little bit out of space, so I'm going to plug the 1 in kind of mentally. It'd be 2 times 1, which is 2. 1 cubed is 1, so it'd be minus 2/3. Plugging in the -1, -1 times 2 is a -2. What's -1 cubed? -1. So this would be -1, making this plus 2/3. Okay, so let's see, I'd have 2 plus 2, which would be 4. And then a -2/3 minus a 2/3 would give me -4/3. I'm going to kind of deviate from my usual notation now, because I'm running out of space. I'm going to think of 4 as being 12/3. And so I get that the area is 8/3. And let's kind of think about whether that seems appropriate or not, whether 8/3 seems like a reasonable answer. Okay, 8/3 is 2 2/3, so a little bit bigger than 2, almost 3. Okay, so a way that we can kind of eyeball this to see if it seems appropriate is if I put a rectangle that goes all the way around this. The area of this rectangle is obviously going to be an over-approximation, right? Because all this piece is missing. Okay, what's the area of this rectangle? 4? I think you're right. 2 by 2. So this area is 4. So does it seem like this would be about 2.67 then? Yeah. So there's some missing here, here, here. I would be worried if I got like 18 as my answer, right? And I'm like, okay, well this this rectangle that's around it has an area of 4, so 18 wouldn't make sense. Should also be concerned if you get negative numbers. I'll talk about that a little bit more. Yeah, pretty much. You could, but you'd probably want to go like check the setup again too. Yeah, and like switch your F and your G. Okay, let's take a look at part B. Okay, so now we're going to find the area between the functions f and g, but now we're given an interval that we want to find the area between them. Okay, so let's see, 0 to 3. Okay, so let's kind of visualize that one. Maybe I'll use red for this one. So 0 to 3. Okay, so on this interval, so from 0 to 1, I'm looking at this area. Gosh, I don't know what's going on with the document today. Make it darker. There we go. Now I got it. Okay, and then up until 3. Okay, so I'm just going to put like a vertical line here at 3. Okay, so again, it's the area between the curves. So basically one curve should be on top, one curve should be on bottom. That's the thing that gets captured. Okay, so that would be this whole region here. Okay, got it. Okay, so with this in mind, are we going to be able to set this up the same way that we did before? Just say the integral from, some top function minus some bottom function? Nice. What are we going to need to do then, maybe? The problem is that at 1, the top and bottom curves switch, right? So from 0 to 1, the green curve's on top and the purple curve's on bottom. But then from 1 to 3, the purple curve's on top and the green one's on bottom. So if I were just to approach this with one or the other, whichever one on top, whichever one on bottom for the entire interval, I'd end up probably taking away area that I don't want to. Okay. So what we're going to need to do then is set this up as 2 integrals. One that represents this area and one that represents this area. Okay, so let's go ahead and do that. Okay, so we'd have to look at the area from 0 until 1. And we're going to be taking the green minus the purple, so it's basically the same thing we had before. 4 minus x squared minus x squared plus 2. That should be in parentheses also. Okay, and then we want to also consider the area from 1 to 3. But now the purple curve's on top, so I'm going to take x squared plus 2 minus the green curve, which is 4 minus x squared. Again, keeping parentheses in mind. Now, what operation do I want to perform between these 2 integrals? Addition, subtraction? Addition, right? Because we want to take this area and add this area, and that would be the total area between the curves. Plus. Okay? All right, so now here's a cool thing. We actually already went through and pretty much found this integral. Well, we found this integral. We found, I should say area. We found this area, right? Now, how would I be able to find this area without actually doing an integral again? Half of it. I can use the symmetry because we know that this is symmetric, this is symmetric. So if this region was 8/3, then the area of this region would have to be 4/3, half of it. Okay, so we're getting that from taking half of 8/3, giving me 4/3. Okay, so I know that's 4/3. Now I could go through, and I feel like we probably are fine with doing this integral, like no problem. It's very similar to the previous one that we did, so to save time, you would go through and find this integral, and it ends up being 40 thirds. Okay, all right, so 40 thirds, and then so we'd add these together, and we get 44 thirds, which is about, if you were wanting to get a decimal, about 14.67. I'll do that one up here too. This is about 2.67. Okay, and it makes sense that this one was a bigger number. It's definitely a bigger region. Okay. You could, if you were wanting to get an approximation, you could probably make a really nice triangle that would be fairly close to the area of that region there. Okay. Okay, how are we doing so far? Good so far? What's up, Raid?
When we do these, do we have to do the integration, or can we just put it in that?
Good question. So I would like to see the integration because that's good practice. If you're going through your homework and let's say you're like halfway done and you're like, oh, I just don't know if I'm going to be able to like get this homework done. I would rather you finish the homework, do all your integral setups. You can use your calculator to find the answer. And then if you have extra time, go back and try to work some of the integration by hand. Does that make sense? So try to do the integration by hand just so you get the good practice. Because I think some of these might even use some substitution. That's great practice, integration by parts, that kind of thing. So if you're really rushed on time, I want to make sure that you at least get all of the concepts of the area down. Okay, so let's take a look at example 2. So now we're going to be finding the area between sine and cosine on the interval from 0 to pi. Okay, so we're going to want to start with, again, another visual, because right now you might be able to imagine which one's going to be on top, sine or cosine. Or is it going to change at some point, I wonder? I think it might change at some point. Okay, so let's go ahead and graph the two to kind of get a visual for that. Okay, so it's on 0 to pi, so I'm going to go ahead and make this pi. Okay, and I know that, I'll make this one purple. Sine of 0 is 0, and sine of pi is 0. And then halfway, sine of pi over 2 is 1. Sure, I'll make that one. Okay, so that would look, sine would look something like this. And then cosine at 0 is 1. What is it at pi over 2? What is it? 0. And then at pi, -1. There-ish. Okay, so it goes same kind of shape. Okay, so there's cosine. And again, we're finding the area from 0 until pi. So now visually I can see that it definitely does change. That is not one curve is on top the entire time. Okay, so we're going to need to, just like up here, we're going to need to break this into two different integrals so that we can find the area between the two curves. Now the first one that gets captured by, so again you're looking for, sometimes people have a hard time visualizing like which thing is the area between the curves. Okay, so you should always have like one curve on top and one curve on bottom. Okay, so for example, like this region right here, is this one of the regions that we're looking at? No, because in this case, one curve is on the right and one curve is on the left. We want one curve on top, one curve on bottom. So if we go here, the green curve is on top, the purple curve is on bottom. So this is the first region that gets captured from 0 to pi. And then the second region would be, again, now purple's on top, green's on bottom, so it would be this whole region here. Now, if I continued with my graph, I'm going to just show you that real quick. If this continued on, which it does, I just didn't draw that part. Okay, they would intersect again. Okay, but I'm stopping at pi. I'm not going to go to here because it says from 0 to pi. So I'm just looking at this region. What if it said find the area between sine and cosine, and it didn't give you an interval?
You just go to 2 pi.
Yeah, well, it goes to 2 pi and then it would repeat, right? So you'd find like this area between the two curves, but then do you see how it would keep going? You'd find an area between those curves, and then between those. Do you see how much area that would be adding up? Your answer would be infinity, because you'd be adding up so much area from, if it didn't give an interval. Because there is no one region that gets captured by sine and cosine. It's a bunch of regions. So, in general, with the trig functions, you'll see a specified interval that you're supposed to find the area between. Okay, so taking a look at this one, we mentioned that the top and the bottom switch at a particular point, right there. Now, just visually, what does it look like? Looks like pi over 4 to me, because it's halfway between 0 and pi over 2. But using my wonderful trig knowledge of the unit circle, I could also find this by just setting these equal to each other. Sine x equals cosine x. All right, what angle on the unit circle gives the same x and y coordinate? Pi over 4, 45 degrees, right here. Okay, so pi over 4 is that intersection point. That's where we're going to be breaking the integral up into two pieces. Okay, so we'd have the integral from 0 to pi over 4. That's our first interval for the region. The cosine curve is on top in this case, so we'd have cosine x minus sine x dx. And then we'd add the integral from pi over 4 to pi. But now sine is on top and cosine's on bottom. Okay, so those would be my two integrals then. Now, since this one involves some trig, I'm going to go ahead and go through and have us evaluate this one. And then I'll have us take a break after that, because I know we've been going for a little while. So let's go ahead and evaluate. Now, again, like in this case, notation-wise, my equal sign would go over here, and I'd have my work over here. I'm running out of space, so I'm going to go here with this one. So I want the antiderivative. Well, first off, do you guys see how there's really no simplification that we can do first? We can't really combine the two, so we'll just have to treat them all separately. Integral of cosine is sine, and then the integral of sine is negative cosine, so this would be plus cosine. Evaluate from 0 to pi over 4, plus negative cosine minus sine from pi over 4 to pi. Do you guys see how this one is just the negative of this one? That should make sense because we just subtracted in a different order, so they're just opposites of each other. Okay, so looking here, we've got plug in pi over 4. I'm going to again do this one kind of mentally, so sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is root 2 over 2. Minus sine of 0 is 0. Cosine of 0 is 1. Plus negative cosine of pi. Cosine of pi is negative 1. So this would be negative negative 1. Sine of pi is 0. Plugging in pi over 4, I would have a negative root 2 over 2 minus root 2 over 2. Okay? You guys with me so far? Okay. All right, so we've got to figure out a way to combine these, get to our exact answer, our exact area. So this would be, so I have two root 2 over 2s, so that would be a root 2. Minus 1. Okay, now this root 2 minus 1, if I just think about that number in general, what does that number represent? Yeah, that's the area of this first region. Okay, would be root 2 minus 1. Root 2 is about 1.414, so this area, the area of this region is about 0.414, which looks about right, because this goes up to 1, this goes to pi over 4, yeah, seems about right. Okay, so then we're going to add, now the next thing is going to represent this region. So plus, and this will be 1, and this will be, well, inside here, this would be a negative root 2, but there's another minus sign, so it's plus a root 2. And I'm seeing that our negative 1 and 1 are canceling. Yeah, giving me 2 root 2 as the exact area of the region. I'll put a little line here to cut it off. Okay, this is about, like I said, root 2 is about 1.414, so this would be about 2.828. Okay. Okay, how are we feeling so far with these? Pretty good. Well, one thing I want to point out here, sorry, I know you guys are like eager to take a break, but while this example is still fresh in your mind, was anyone kind of concerned about this one being below the x-axis and thinking maybe we should treat it differently at all? Well, you might not have been thinking that, but I'll explain it anyway, because that's what I do. The reason why this is a negative area, yet we're adding the area, is because we're taking the area under the top curve, which would be, so the integral from pi over 4 to pi would be this part, right? Just the area under the purple. Well, actually, it would include that too. Okay, so when we subtract the area of cosine, if I were to think about splitting it up here, which I don't have to do with the integral part, but just visually, with this section, I'm taking the area under the purple and subtracting this area to give me this piece here. With this one, I'm taking the area under the purple, and then I'm subtracting the negative area here. So what am I really doing then? Adding it. Okay. So the cool thing about the area between curves is even if you go below the x-axis, you actually end up creating more area because you subtract that negative and create even more area in the region. James?
Can we